Hi guys, and welcome to this lesson where we are going to look at number sets. Now, what do I mean when I'm talking about number sets? Well, it's actually very simple. A number set is basically just a collection of numbers that have a certain property. And the first number set that we are going to look at is called the counting numbers. Okay, so what property does the counting numbers have? Well, very simple. Will you count for me, please? Okay. You'll go 1, 2, 3, etc. Okay, so what do we notice? How do you count? Well, when you count, you start at 1. That's very important. Counting numbers starts at 1, and then the increments are 1 each time. In other words, we're counting in whole numbers. 1, 2, 3. So counting numbers are basically whole numbers starting from 1. Now, the symbol that we use for counting numbers is the symbol N. Okay, that represents the counting numbers, or another way of calling it is natural numbers from from 1. You'll see now why I call it natural numbers from 1, but simply it's the counting numbers. Now, what is this all about? Okay, that funny N thing. Well, that's just a shorthand to show that we are using a collection of numbers that start from 1 and they're whole numbers. So, for example, if I tell you in maths that I have a number from the counting number set, one way of writing it is like this. Some number x is in or an element of the set n. This means that x can be any number in the collection of counting numbers. Okay, now another set of numbers is called the natural numbers. Okay, so we heard that in a moment ago. The natural numbers are basically the same as counting numbers. The only difference is we start at 0. Okay, in nature, that's why I'm saying natural numbers. In nature, whole numbers occur. So, for example, I can have 1 tree. I can have 2 trees, I can have 3 trees, okay, but I can also have no trees, 0 trees. So I have 0, 1, 2, etc. Okay, and so the natural numbers are the same as counting numbers. They're whole numbers. The only difference is we start at 0, and the symbol is exactly the same. It's also this little N with a funny double line in the beginning. Okay, but we have a little footnote, a 0 footnote, showing that we start at 0. Okay, next we have the integers. Integers. Now, what integers are, they're the same as counting and natural numbers, but they include all the negative numbers as well. So they're whole numbers, okay, including the negative. So we have negative infinity, whatever, as long as it's a whole number, -3, -2, -1, 0, 1, 2, 3, etc. Okay, now the integer symbol for the integers is a little z with a double line for this diagonal part of the z. Okay, so far so good. Now we've looked at all the possible type of whole numbers we can get. Whole numbers obviously being numbers without a decimal. So what if I do have decimal numbers? Well, there's two types of decimal numbers that we get. We get, for example, the rational numbers. Okay, now a rational number, first of all, well, let me write it like this. A rational number is any number that can be written as a fraction. So now a rational number is any number that has a numerator divided by a denominator where n is an element of the integers and d is an element of the integers. Okay, notice how I've been using, or how I just used this mathematical way of expressing that a rational number is a number that can be written as a fraction, where my numerator, that's what I'm writing here, is an element of integers. In other words, it's some integer value, and my denominator is some integer value. So let me look at a few examples. I think that will best describe it. So, for example, the number 2. That's a rational number. Why? Because I can write it as 2 divided by 1. Okay, that's a rational number, 2 divided by 1, where 2 is an integer number, it's a whole number, okay, and 1 is a whole number. If I look at a number like 3.5, negative 3.5, the number negative 3.5 can be written as negative 7 over 2. Notice that negative 7 is an integer and 2 is an integer. Okay, we can look at a number like 0.33, or actually let me write it this way around. Okay, if I have the number 1 over 3, a third, this is the number 0.333 recurring. Okay, so the number 0.333333333 to infinity is 1 divided by 3. Again, we've got we've got integer divided by integer. That is again a rational number. Okay, so I just want to show you here for this part, so we can see all whole numbers, all integers, okay, will be rational. And here I can see that all finite decimal numbers will also be rational. Finite decimal. That is not decimal. Okay, decimal. Okay, all finite decimal. So for example, if I have a number like 0.0101, okay, the way in which I can write this as an integer divided by an integer is I just take the whole thing without the comma, okay, without the that would make it 00101. Now the 00 in front is meaningless, so I'll have 101, and then I divide it by where the comma is, I'll put a 1, and then for every decimal place I'll put a 0, 0, 0, 0, 4 zeros, because there's 4 decimal places. And if you punch this into your calculator, you will see 101 divided by 10,000 will give you 0.0101. In other words, I was able to write it as an integer divided by an integer. Brilliant. So any finite decimal place will work the same. If I've got 100 decimal places afterwards, I will take everything without the comma as the numerator, and I'll divide it by 1 with 100, or what did I just say, 100 decimal zeros. I'll divide by that. Okay, now the only point I'm trying to make is that any finite decimal will be a rational number. Any integer will be a rational number. The problem occurs is when I have infinite decimal places. Okay, infinite decimal places will only be rational if they are recurring. Okay, if it's a recurring decimal place like 0.13478133478, okay, yes, there isn't an easy pattern as there, but it's still not very difficult. It is recurring. I've got some sort of decimal place that's recurring itself. Now, whenever you have that, and in front can be anything, of course, but whenever at some point my decimals are recurring, this is a rational number, and the symbol for rational number is the symbol Q. So that is for rational number. Now that brings us to our next number, which is now irrational numbers. Now an irrational number is obviously a number that is not rational. Okay, irrational is simply not rational. And if we look at our definition for rational, it's exactly the opposite. So all integers is rational. So irrational numbers do not include the rationals. Okay, all finite decimals is rational. Okay, so they can't be irrational. The only difference comes in with these recurring. We'll see that irrational numbers have non-recurring, because if it is recurring infinitely, then it is rational. So it must be non-recurring infinitely, or let's just say infinite, non-recurring infinite decimals. And a few examples would be something like the square root of 2. The square root of 2, let me get that, is 2 square root, okay, 1.41421. Do you notice there? I'm sure you can see 1.414213563. Can you see that there is absolutely no pattern yet? Wait, there's 8, but oh man, okay, absolutely no pattern. That means that this would be an irrational number. Now, basically what that means is that there's absolutely no way of writing this as a fraction. Okay, there's no way of writing the square root of 2 as a fraction, and there's a way you can actually prove that. Again, I did that in my second year of studying pure mathematics, so it's definitely not for this course, but there's a way to prove that the square root of 2 cannot be written as a fraction. Okay, so that's one example. Another example is pi. Okay, pi is the ratio of the circumference of a circle divided by the diameter of a circle. Now you would tell me, but wait, doesn't this mean that if pi, and by the way, pi is the ratio 3,1415, etc., etc. Let's get it. Pi 141592653. Again, notice that there is absolutely no pattern after this comma, so pi is also an irrational number. But pi is the ratio of the circumference divided by the diameter. Now, now you might tell me, but doesn't that mean that it can be written as a fraction? And yes, it can be written as a fraction, but not in the sense of rational numbers where the numerator is a integer and the denominator is an integer. In this case, either one of the two, either the circumference or the diameter, would be an irrational number itself. So if I, for example, take a rational radius, like the radius of 8, and I draw a circle, which is obviously not what this is, but assume I am, taking a diameter of 16, draw a circle with that diameter, then the circumference will definitely be an irrational number. Okay, so these numbers do actually exist in reality. The square root of 2, for example, is when I have a length of 1 making a 90 degree with another length of 1. So for example, from here to there is 1, and then 90 degrees from here to there is 1. If I now measure this distance, okay, that distance will be the square root of 2. Very difficult to measure that, because how do you measure something with infinitely decimal places? But mathematically, this must be the square root of 2. And you'll learn later maybe why that is so. Okay, when it comes to the theorem of Pythagoras, if you can't figure it out by yourself at this stage. But nevertheless, the reason why I actually just showed these two points here, or made this point here, that these numbers exist in reality, is because these two types of numbers together make up what is called the real numbers. So real numbers are all the rational and irrational numbers together. But the actual definition for real numbers, well, I don't know if this is the actual definition, but this is what I would say it is. It is numbers that will give a positive when squared. Okay, a number that will give a positive when squared. What do I mean by that? What I mean by that is if I take a number and I multiply it by itself, I will get a positive answer. Okay. I should get, if I have a real number, then I will get a positive answer. Sorry, I wrote it weird now. Okay, so if I take any number and I multiply it by itself, another way of writing that is saying x squared. That's why I say when squared. Squared means I'm multiplying it by itself. Okay, so when a number is squared, then and I get a positive answer, that is a real number. So for example, if I take the square root of 2, the square root of 2 times the square root of 2, the answer is just 2. It's a positive answer. Even if I take negative square root of 2, which is an irrational number, and I square it, okay, the negative times the negative will be a positive. Okay, and that's the point. When a number is squared, then the negative part will multiply itself and give a positive. Okay, these are called real numbers. So what if I do have a number, some number that I square and I get a negative answer? Okay, like what can I square, what can I multiply by itself and get a negative answer? Well, there's no real number, okay, because all the real numbers, all the rational and irrational numbers together will always give you positive. So this must be an imaginary number. Okay, imaginary numbers. And I just realized, so sorry for interrupting my train of thought there, I didn't give you the symbol for the irrational numbers. But irrational numbers is simply not rational. The rational symbol is a Q, okay? As I showed you here, the rational symbol is a Q. And if something is not rational, we put a little accent there to show that it's not rational or irrational. Okay, the real numbers symbol is this R I made here. Sorry, I don't think I emphasized that. Here's the symbol for real numbers. Okay, so and why I showed you that is because imaginary numbers, okay, is all the numbers that are not real. Not real. In other words, we'll take the real numbers and give it a little accent to show that it is imaginary. Okay, so imaginary numbers are all the not real numbers, and they are numbers that when I multiply them to itself, I get a negative answer. Now, the most basic and the fundamental of the imaginary numbers is the square root of -1. That as a number, if you try and punch that into your calculator, it would give you an error because the calculator cannot work with that number in its normal functions. Now, imaginary numbers we don't use at school level, or at least not for this course, and you will encounter them at university. If you continue with any sort of maths at university, you will encounter them. That's why I put them here, so don't get a fright when you see them. It basically just, they're numbers that when I multiply them I get negative answers, and we use a little symbol I for the square root of -1 called the imaginary unit. Okay, now these two together, real numbers and the imaginary numbers together, are called the complex numbers. The complex numbers are it uses a C, and again these last two is not so important, but the complex numbers would be all the numbers, all the real and imaginary numbers together. Now I just want to lastly just show you a Venn diagram. A Venn diagram is just a way of putting different sets, we're talking about number sets, displaying them in a pictorial way or in a diagram. Okay, and basically what this is just a graphical representation of these sets. So imagine I had a bowl here, and in this bowl I had all of the natural numbers. Okay, so make it look a bit more like a bowl. Okay, so here I have all of the counting numbers. The counting numbers. In other words, I've got the number 1, 2, 3, a whole bowl full of counting numbers. Now, if I wanted another bowl, and in that bowl I wanted all the the natural numbers, I would need a slightly bigger bowl, only slightly, and I'll put the natural numbers, the counting numbers in that bowl. So now here's all my natural numbers, and the only number that's in the natural numbers bowl and not in the counting numbers bowl is the number 0. Okay. Now, if I wanted a bowl with integers in it, I would put the natural numbers in that bowl, which already includes the counting numbers. So here's my integers bowl. Okay. Now all of the numbers that would be in the natural numbers but not in the integers would be natural numbers, but all of the numbers that are integers but they aren't natural numbers would be negative numbers, like -1, -2, -3, etc. They won't be in the bowls inside. Okay, and then we have, after the integers, we had rational numbers. Now all of the integers were rational numbers, so if I had a bowl, with all the rational numbers in Q. Inside the rational numbers bowl, I'll have to put the integers, which contained the natural numbers, which contained the counting numbers. Okay, but outside of the integers bowl, I would have any decimal numbers, anything that can be written as a fraction, n over d. I use n and d because the one is numerator and the one is denominator. Any numbers that can be written like that, okay, they are in this bowl, but that includes these. So things that's not in here is any decimal number, any decimal digits would be in here. Okay, and then when I have a bigger bowl, okay, here I've got a bigger bowl. In this bigger bowl, I'll put all the real numbers, and the real numbers include the rational numbers, but it also includes irrational numbers. So the irrational numbers would be the numbers that's outside of the rational numbers bowl, and that would be numbers like pi, square root of 2, square root of 3, cube root of 2, or anything that doesn't have a cube root. Okay, these would be the irrational numbers, and that's where we're going to stop. Irrational numbers would be numbers that's not rational. That's where we're going to stop, but there would be a bigger one called the complex numbers, which are all the real and the imaginary numbers. But let's stop it here. This is the Venn diagram. That's as much as you need to know when it comes to number sets, and I hope this was a simple enough question for you to, or topic for you to understand. We'll see you in the next video.